Just looking at my share screen here. Sorry about that. Okay. And video. All right, fantastic. All right. So thank you everybody for joining me today. And thank you, Mark, for giving me the platform and the opportunity. As you said, my name is Joseph Broz, and today I'm going to be talking to you about analog quantum simulation. And I just want to emphasize here that I'm really open to more of a discussion format here as well, or I have like a presentation to give, but if people want to interrupt and ask questions or have discussions, I'm totally cool with that. The main thing that I'd really like to convey today is going to be sort of a fairly new idea I have, and haven't had a chance yet to implement experimentally. I've had it just over the last month or so, and I'm pretty excited for it. I think it's pretty interesting. So if I'm not doing a good enough job explaining it or anything like that, please let me know, because I'd really like to, potentially stoke some interest or potentially get somebody interested in collaborating. So with that, I'll get started. Here's the group. This is actually a little bit of an old picture, but it has, I don't have my mouse, do I? There we go. It has pretty much everybody that's working on the project that I'm doing now. And that's my PI, Hartman Hafner, my postdoc, Wei Ting Chen, and our theory collaborators, Brigitte Whaley at the Physical Chemistry Department and Mohan Saravar. And in Hafner's lab, we do a lot of different types of experiment, generally revolving around quantum information science, including some more traditional quantum computation type stuff, but also a lot of sort of off the wall things. Like we last year, our group trapped electrons in a fault trap for the first time ever. So I think that's pretty cool, especially given that I think in the inaugural talk you gave, Mark, you made this comment, or you made this comparison of ion traps to superconducting circuits. You mentioned that ion traps have great fidelities and long coherence times, but they're slow, like 2 orders of magnitude slower than superconducting circuits currently, when you compare the fastest to the fastest. But the reason they're actually so slow is because the way that we entangle ions, the way that we communicate information from one ion to another, is actually by their motion. They're charged, and we squeeze them together in a trap. And if one ion is moving, then it pushes on the other ion, and that's ultimately the mechanism that we use to entangle them. And so if we trap electrons, they're 5 orders of magnitude smaller, or lighter. And so we would be able to bridge that gap. But there's a ton of technical challenges there. It's not even clear that that's possible to, so we've trapped, but it's not clear that we'll be able to process with them. And also, I just wanted to highlight another, so I didn't work on that project specifically, and this is another one I didn't work on, but I wanted to highlight it because I think it's really cool. This is an actual image of a ring trap configuration that we have. So each one of these bright lights here is an actual atom. And what you're seeing is the light scattered. We're shining laser light on it. It's actually being scattered off, and we're imaging it in real time using a CCD camera. And so what's cool is that we can actually take this thing and spin it and control its rotational motion. And so last year, there was a paper that came out from our lab where we actually coupled the internal electronic degrees of freedom of the calcium atoms to the rotation, the higher angular momentum rotational modes of the rotor. And I just think that's a super neat, cool sort of interaction that it's sort of fundamental in introductory quantum mechanics when you're taking it in school, but I don't think has been implemented that, in super coherent systems like trapped ions before at this level. So I'm very excited and interested to see what happens with that. But as for myself, I'm currently working on primarily a quantum simulation in sort of this 3D trap here, which is a little bit of the older technology, like the Buick Regal or the Lincoln Town Car of trapped ions. And so it's very reliable and allows us to kind of just think up cool things to do with it instead of getting bogged down the technical challenges. With all that being said, let's get started. So quantum simulation, there's a ton of review articles on this, so I just kind of grabbed a definition from one of them that sort of works. everybody kind of knows what you're talking. This is not as rigorous of a definition, I would say, as quantum computation. Everybody kind of has a different definition that changes from talk to talk or from intention to intention. But basically any quantum system precisely prepared or manipulated in a way aimed at learning an interesting property of another complex quantum or classical system. I think that's a fairly broad definition and matches most of the ones that I've seen. And so to just show that in sort of a pictorial view, you take some complicated system over here, you distill it into some model, which is an important thing to mention because your model might be wrong, and that happens quite often when it actually comes to implementing these things. You plug it in your quantum simulator, your quantum device, and importantly, that thing needs to be tunable. Otherwise, there's no advantage here. So you need to be able to really have enough, not full control, not the same, you don't necessarily have to have this full control of a universal quantum computer, although those can also do quantum simulation, are very promising for that application in the future. But the point is you just have enough control that you can sort of tune some parameters, see what the system depends on, what it does, and hopefully try to, at the end of the day, learn something. And this is really like a real world example here. This is something that Microsoft likes to talk a lot about, but this is the FemoCo, I think. It's something that you find in bacteria, or part of a molecule that you find in bacteria that is responsible for doing this thing called nitrogen fixation, which basically converts ambient nitrogen to ammonia. And what's interesting about that is they do this pretty easily at room temperature, but currently in the industrial world, we're using the same process that we've been using for 60 or whatever years. And it eats up 2% of the world's energy every year, and something like results in something like 4% of the world's global carbon emissions. So solving this there's a huge incentive to solve this problem. And if you look at it, it doesn't look terribly complicated. But it turns out that our best computers and our best computational devices cannot solve this, cannot explore the parameter regime of this thing well enough to even understand and figure out how bacteria have solved this problem. So we know there's a solution because evolution has figured it out for us. So this is just one potential application where a quantum simulator or a quantum computer would potentially be able to really have a major impact in the world. So what can quantum do? I think so far in these meetings, we've had a lot of sort of descriptions of basic quantum mechanics. So I don't want to bog you down too much with this, but just in case you're joining for the first time or rather recently, I'll give a quick description. So, basically a classical bit can have either a value of 0 or 1. I think we're all pretty familiar with that. And it really is like, if there's no error there, it really is the smallest possible unit of information in like the Claude Shannon sense. Like if I wanted to learn something about you, I can ask you yes or no questions. And that's, if you give me anything less than that, if you just answer yes all the time, or you just answer no all the time, then I can't learn anything from it. So it's the simplest sort of possible system that we can imagine making that's non-trivial in the classical world. So what's the direct analog for that in the quantum world? It's a quantum bit or a qubit. So on the surface, when you look at it right here, it can also, take the value of 0 or 1. We put these little fancy brackets around it just to let you know it's quantum. But where things get really weird is the fact that it can also exist in a superposition of both 0 and 1 at the same time. And so if you actually look at these, we have two parameters here, p and phi, and they can assume any real numbers. So just to try to describe this thing with the classical computer, you would need something like 100 bits, depending on how precise you are. And just by looking at this, it already looks really complicated, right? We have square roots and exponentials and complex numbers. So this is the simplest possible quantum system. And so what I'm trying to sort of inspire here, in case you're less familiar, is just that quantum mechanics is fundamentally more complex. That we can definitely say without any doubt. And we also, for the most, if you talk to complexity theorists, they'll tell you that we can't actually prove that quantum computers are faster than classical computers in a rigorous sense for practical problems. I think there's been some work done on sort of impractical problems, but everybody believes it's true. So a natural question is to ask, why would quantum simulators be useful for simulating other quantum systems? specifically, as opposed to classical systems. And so what I want to kind of give you a sense for right now is how quickly the complexity of a system of quantum bits or quantum systems grows. So this is how we described a single qubit. But if we want to describe 2 qubits, this is what it looks like. If we want to describe 3 qubits, this is what it looks like. It's just blowing up already at 3 qubits. And this is actually exponential in the sense that n here is the number of qubits, and this shows up in an exponent. And so if you haven't developed like an intuitive sense for super polynomial growth, it can really be hard to grasp your head around. If you look at this plot here, we go up to like, this is 10 qubits, the amount of classical bits that I would need, just classical parameters I would need to describe it, and you're already at 2000. And to steal one of Sonika's slides, if you go to 300 qubits, then the description would already require more bits than there are atoms in the entire universe. And I'm not a theorist, but I always think that this is like a really profound fact, because it's just that somehow all of the amount of information, even though it's not information that we can necessarily get access to in the physical sense, but somehow the universe is keeping track of an amount of information that is just unimaginably, astronomical isn't even the right word because it's bigger than any scale in the astronomical world, but somehow keeping more track of more information than all of the physical things that we have access to in the world. So I don't know what to make out of that, but it's just something really crazy to think about. So in other words, if I wanted to simulate it, if I wanted to make a new universe, I would have to keep track of all that information. And so that kind of leads into the original motivation for quantum computers. And everybody has seen this quote, I think, at this point. I think, Mark, you had this in your talk, and I think a couple of other, Ben Cordier, I think you also had this in your talk, but basically, Feynman made in this sort of, it was a keynote speech that was transcribed and published, and he made this point that essentially the same point I just made, that classical systems are fundamentally ill-equipped to describe quantum systems. There's something wrong there. It just doesn't make sense. It makes you think that the proper way to actually describe the universe is by using quantum mechanics, which is not so surprising. But I just wanted to point out here that if you actually look this up on Google Scholar, this is organized in order of the number of citations received. And all of these right here are textbooks or lectures. So, this was a keynote speech, but it was published. This is technically Richard Feynman's most cited scientific work, which is really mind-blowing, because if you're not familiar with the guy, he was a really, one of the most brilliant minds of the 20th century, pioneered quantum electrodynamics and path integral formulation of quantum mechanics. Yeah, I think this is, we often get insight into how interested people are in quantum technology and quantum computers by talking about how much people are investing, or how much people are putting, how much funds are going into it, or how much startups are popping up. But this is sort of like the academic side of the story. Citations are also, through the roof. I know this from experience, because if you pick up a thesis in my field in trapped ions that was written anywhere within the last 10 or 15 years, there's probably like a 50-50 chance that you're going to find this quote or a very similar quote within the first chapter or so. So I wanted to give just a general idea of digital quantum simulation for dynamics, just because I mentioned this in the abstract. And I say something that's maybe contentious, which is that digital quantum simulations won't be useful until we have fully fault-tolerant computers. And if you consider something like VQE, which totally reasonably should be considered a simulation, then these are one of the most promising things that might actually accomplish a real improvement in the NISQ-era. At least we believe they will. I don't think we have any kind of rigorous proof of this at this time, or other optimization algorithms, even ones that tackle classical problems, more so classical problems. But one place where that statement is true is the sense that Feynman was originally thinking about, which is simulating dynamical problems. So in quantum mechanics, you have something called the Schrodinger equation, whose formal solution looks like this. And you don't have to worry about the details so much if you're not math inclined. But the point is that this parameter H here is a matrix. And we just saw how quantum systems get exponentially large with the number of qubits. And so it's extremely difficult for us to exponentiate very large matrices. And so this is really at the core of what's so difficult to simulate these problems. And that's assuming a time independent problem. It gets much worse if we have time dependence. But the idea is, if I wanted to solve for this evolution, this is what I need to do. Exponentiate this and get some function of time. And then what I can do is plug it in and just use it as like a standard gate to go from psi of t0 to psi of t, or interpret it that way, I should say. So in general, no method exists that's sufficient to simulate this with quantum computers, which is as to be expected. If this is true, I mean, the Schrodinger equation fundamentally describes all of non-relativistic physics. So if we could do this, that would mean that universal quantum computers would be able to solve all problems that describe the world efficiently. But it turns out there's a large class of physically motivated Hamiltonians consisting primarily of local interactions where there is a guaranteed efficient way to compute these. So and by the way, this is like very natural. Like the local interactions, just it means that things have to get close to each other to interact with each other, and most of the interactions that we see in the world are based on how close things are. Because potential energies and the force laws fall off very rapidly with distance, and so this is just very natural. If you have a very large system of quantum objects, then the chances are some object over here and some object over here, if they've been interacting with each other for a while, they might be entangled, through mediating interactions. But all we care about is that the interactions themselves that are happening are just locally spaced. And so what that means in practice is that I can decompose this big H into a sum of these smaller Hamiltonians. And the point here is that if I can then efficiently exponentiate this and solve for, a sort of find a combination of gates that can do this in a sort of an efficient way. So you can definitely find one that goes in an efficient way, but like maybe a particularly efficient way for when it comes to NISQ-era devices or even slightly post-NISQ devices, then you can solve this problem pretty easily. And here's just an example of how this works. It's really very simple. There's just this Lee-Trotter product formula that tells you that, so in general, if these weren't matrices, but these were scalars, we know from the law of exponents from high school that we can just always do this, factor them out like this. But it turns out that when it comes to linearity, when it comes to matrices, this isn't true. So a mathematician would say that this is a consequence of the fact that in general H1 and H2 don't commute. As a physicist, you might say something about the Heisenberg uncertainty in principle, but either way, the point is I cannot go from here to here, and that's sort of a problem. If I could, then every time I had a Hamiltonian in that form, I could always solve it easily. But there is this nice formula that allows us to sort of break everything down into smaller and smaller steps, and we can know that as an end approaches infinity, this becomes precise. And so the whole idea behind trauterization for doing digital quantum simulations of dynamics is just to do this, to sort of stroboscopically switch between H1 and H2, and if you had many more of these, and H3 and H4 or whatever, and the number of gate scales is k cubed e squared over epsilon, where epsilon is the error. And so this was like something that was proposed by Lloyd a million years ago, and there's been a ton of, even though I would say that dynamical simulations kind of fall into the compared to some other interesting simulations that people are thinking about, like more adiabatic type things and more solving for global minimas and that sort of thing, general optimization problems. People put a lot of effort into this, and there are definitely certain problems where they can find better and better ways to do this, but there's a lot of question of like, okay, if you can find a better way to solve it that's more efficient than substantially more efficient, does that just mean the problem itself is fundamentally easier to solve and stuff like that? There's a lot of interesting work there in case you are interested. And one of these papers, or one of the, some of the people that are sort of prominent in that area, posted some of these facts in one of these papers, which is that So the best estimates for dynamical simulation of a next nearest neighbor Heisenberg model with 50 spins right now is 50 qubits, 10 to the 8 entangling gates, 10 to the 9 single qubit gates. So the circuit depth is, I would say, out of reach for NISQ-era devices at this point, in my opinion, by a long shot. So I don't think this will be practical until we have a low noise computer with, depending on your quantum error correcting code, 10,000 physical qubits. So that's a little bit of a ways away. If you're really optimistic, maybe 10 years, I've heard on here. If you're less optimistic, maybe a little bit longer. But you just got to point out that for 50 spins, we're not even really at the point yet. We're just solving that problem. Can't be done on a supercomputer. That's kind of right there at the edge, but there are clever ways, and people could almost certainly solve this. Now, maybe 100 qubits, but so the point I have with this is that there are at least some instances where digital quantum simulation is not really going to be viable until we get into post-NISQ-era. And in that case, then maybe I think that it'll be like one of the first. I think that there's a lot of really interesting things that we can do just with a couple of hundreds or thousands of logical qubits, which might not be true when it comes to, implementing Shor's algorithm. But there are definitely certain areas where this isn't going to be useful for a long time. So an alternative is analog quantum simulation. And, I'm just going to give a general description of this. Analog quantum simulation is, in my opinion, a purpose-built quantum device that leverages its native interactions to run continuous time calculations. And probably the continuous time calculations part is the real definition. But the whole point for making these things useful is the idea that you might have some quantum systems that are working towards achieving the level of fidelity, control fidelity, measurement fidelity, or whatever else to actually compete as quantum computers, or maybe not. Maybe they're more academic, institution, pure research things, particularly like some neutral atom experiments that are out there. But a lot of these systems have really, really nice features where, for example, you can already trap millions and millions of qubits, and you just don't have as good of a local control on them. You don't necessarily have the same ability to measure, do full quantum state tomography if you so choose, regardless of the scaling of that. But there's a lot of hope here that we might be able to do a lot of interesting things because people are trying to use these types of systems, these large arrays of neutral atoms, for example, to explore things like high temperature superconductivity. And when it comes to that, it's reasonable to imagine that there should be sort of robust, we're trying to find something that sort of exhibits quantum features even at room temperature or higher temperatures. So I think there's some hope that you don't need to have the full control overall of the system, and as long as anyways, I won't go any more into that. But, and I just want to point out some of the downfalls that are very obvious for analog quantum simulation. And one is that there's no general scheme for error correction. But I do point out that you can build up confidence in the results. So we have a paper that's in the archive right now called I think randomized benchmarking protocols, but it's one of these things that sort of just thinks of the obvious things that you can do to build confidence in an analog quantum simulator, even if you have no hope of doing error correction. And the ideas are pretty simple. Like you go forward in time and then you go back in time, and you should end up in the same place. And that sort of gives you some insight into the errors that are in the system. Then you can be more clever and go forward in time and maybe rotate a basis, and also go back in time in such a way that you should end up in the same the same state that you started out in. And then if you really want to be clever, you can kind of like break up your Hamiltonians into the local components and randomize them and compile some random way to go forward and some random way to go back, which is in a very superficial sense related to randomized benchmarking from more digital quantum computation. But these are just some ideas. Also, if you had a really useful analog quantum simulation right now, you can imagine people are really interested in, you can imagine that that would promote somebody from a completely different platform to try to implement it. So if I was doing, if I came with a really great analog simulation in trapped ions, and people were really interested in it, but they weren't completely confident, another way that you could build up a ton of confidence is to have somebody, completely independently, maybe on the same platform or a completely different platform like superconducting circuits, run that same sort of analog simulation. And if the results sort of start to coincide, you can build up a lot of confidence. And this is really just the way that experimental physics has sort of always been done when it comes to doing precision metrology or anything else. So I just emphasize that. So I emphasize this because there are a handful right now of experiments that are out there and have been for maybe at least the last 5 or 6 years that arguably have demonstrated quantum advantage as far as we know, in a sense that we don't right now, as far as we know, have any computers that can calculate up to the point that they have, whether it's time dynamics or whatever else. It makes sense. It makes sense that they get less attention than these certifiably difficult things that people at Google and China are doing. But at the same time, these are potentially much more practical things. So I think there's I think sometimes maybe analog quantum simulators get a worse rap than they really deserve. And I would just also mention, and I didn't have a chance to list these, but there's a lot of interesting theory work also. It's a fairly active field, which I kind of saw when I was looking up stuff for this presentation. They have, somebody just came out with a proof of, in some sense, universality of an Ising interaction in the analog quantum simulator, which I thought was really interesting. And Jen Zeiser has come up with some notion for how to actually do, in some really crude sense, an analog simulation that has a result that you can verify with sort of local measurements, so that you don't have to actually solve the thing itself. That is under certain very reasonable assumptions, similar types of assumptions that were made in China and in Google, that you could achieve quantum supremacy with analog, in this case, dynamical simulation. Okay, so now what I'm going to transition to is talking about the analog simulation that I'm actually working on right now. And so again, I've sort of very recently developed an idea on this that I wanted to kind of share here, just in case people wanted to get involved with it or collaborate on it. I'm still not entirely sure what to do with it, but I have a lot of hope. But basically here what you're seeing is an image of the actual ion trap. I think this is the actual ion trap that I'm using right now to trap ions in my lab. And what you're seeing over here is sort of they take a lot more space than that, but you're seeing some sort of indication of where the ions themselves are actually trapped. And then what you see here is an actual real image of a large number of ions trapped in our system. And I would just think this is cool. Again, I mentioned this with the ring trap, but each one of these little blinking lights here is an actual individual calcium atom. And I always thought this was so cool when I joined our lab. I still do, because you can sit there and our lasers are focused well enough that you can actually point them on individual atoms, and you can sit there and see them go through quantum jumps and get dim. And I just also want to sort of emphasize here, if you look at this, you see that the spacing over here at the ends it is a lot larger than it is in the center, and that's just a natural consequence of the fact that these are ions. So we trap ionized atoms that have a net electric charge in RF and DC fields. And so what that means is that this ion over here is feeling all the Coulombic repulsion of all these ions. They all have the same charge, and so that's why it's getting pushed a little bit farther away. And that's an important point, again, because the fact that these things push on each other is really like the quantum bus or the quantum wire that we use to generate entanglement to build things like CNOT gates. Okay, so I'm going to give a very, very brief abbreviated idea of how we actually trap ions in the lab. This is going to be sort of quick, down and dirty, but please ask questions if you have any. So how can we trap an atom? So one of the oldest and most robust methods is to simply ionize it, like I just mentioned. strip off the outermost electron, and then use strong electric fields for confinement. We're very good at controlling electric fields and stabilizing electric fields. So this is something that people have been doing for a very long time, and I think that we understand pretty well. And I think that's a major advantage as compared to some of these more exotic trapping techniques like optical tweezers or optical lattices. The atom that we use in our lab in specific is an isotope, this isotope of calcium that has no hyperfine structure. So we address everything optically, and we do have finite lifetimes on our qubits, which is not the case for everyone. But some other options are terbium. I know that's what is used by Chris Monroe, and an ion cube, beryllium, magnesium, strontium, etc. There's a wide variety. So if I want to trap this thing, I run into a problem that the laws of nature fundamentally prohibit me from trapping a charged particle with static electric fields. And sometimes you'll hear people call this Earnshaw spectrum. So basically the best that we can do is create this thing that, this quadrupole potential, which looks like a saddle. And what this is actually showing is the electric potential landscape. But the way that you can interpret this is the same way that you would naively interpret it if you were working with gravity. So it's a saddle, the ion is trapped along here, but it wants to fall down over here. So the way that we get around that actually is to basically just flop it. So we just oscillate this thing at RF frequencies. And because the ion has some inertia, because it's massive, there's some, finite response time. So it gets caught in this area. As soon as this thing goes down, it starts to fall. But before it has a chance to go very far, it gets caught again, then falls. And so if we do this fast enough, then we actually get something that the time average effect looks like a harmonic potential or a bowl, something that can actually trap that ion, that electric charged particle in a minimum. And so that's just the general idea there for trapping ions. It's fairly simple, but extremely important. So the guy that came up with this, the Wolfgang Paul, which is why you'll hear people call them, Paul traps or linear Paul traps, actually got the Nobel Prize for this. And obviously it's very useful for us for trapping ions and building ion trap quantum computers, but it's also used very frequently for doing atomic mass spectroscopy, basically. Okay, so now that we have the ions trapped in this bowl or this well, if we push on them, they can vibrate. And so again, I'm emphasizing this point that if we have two of them, then they vibrate, but they also push on each other. And so again, this is how we generate that fundamental interaction that we use to get entanglement. This is, again, the quantum bus for trapped ions. And the ion's vibrational motion is actually quantum. So we would call it a quantum harmonic oscillator. And, if you've never heard of this before, if you're not coming from a physics background, the point here is that if each one of these levels is a potential energy level, it's discretized, but each one of these energy levels is a potential energy level that the ion center of mass can occupy. And so the emphasis is that this is much more complicated in some way than a qubit. And we get very high finesse, very high quality harmonic oscillators just by default in a trapped ion setup. So this is some impetus or some inspiration for thinking, hey, we could actually use this as a quantum resource, maybe not in the context of quantum computing directly, but if we're willing to sort of relax things and go down the analog route, maybe we can do some really complicated, cool simulations or calculations with much less physical resources. And so just, like I said, they're characterized by an infinite number of equally spaced energy levels. And just to make that last point that I gave a little bit more precise, people think about mapping qubits. People think about mapping harmonic oscillators to qubits like all the time, because if you want to do something like a digital, quantum simulation of these lattice gauge theories or whatever, you need to be able to handle bosons. And so I was just reading some recent literature where the claim was for, like a full parameter regime, you need 6 to 7 qubits, which they felt was a pretty big accomplishment, and it also scales linearly and is efficient. So it's a major accomplishment, but to do a simple operation on just that harmonic oscillator, so like to push it to do like an X hat operation, or like to couple to its position, the same, something equivalent to like doing a T gate on a single qubit, takes 10 to 100 C naughts, depending on what you're doing, what your implementation is. So that means just to sort of simulate a single one of these things on a digital computer right now using this trauterization or something similar, something better, is already kind of pushing what we might be able to do with the best digital computers we have right now. So again, this is sort of inspiring us to think that maybe these harmonic oscillators that we have are a really good tool that we might be able to use right now to do some really cool stuff that might be able to outperform what we can do on a classical computer. So fundamentally, the way that we store information in ions is by talking to the electrons in the outer shell, and basically we can shine lasers on them and promote them to higher energy levels. And so this is like a typical operation that I do in the lab every day, where I just shine a light on it. The frequency of this guy is actually resonant with the splitting of this level, and it's very sensitive to that. It has a very high Q. But this is basically how I can take a 0 to a 1 or anything in between. So I can create that state that you saw earlier, the square root of 1 minus p, 0 plus p, the square root of p to the EDI phi. I can choose any arbitrary parameters that I want and basically initialize the system just using a laser shine on ion like this. And so this is just like an picture of our lab, which is kind of, my experiment is kind of thrown together a little bit, but this is all the cool stuff that we have in here. This is the actual trap right here that you saw earlier. This is the vacuum chamber containing it, and this is where I do all my quantum computation experiments. And I just wanted to point out this thing is held together with like duct tape, and loose paper, and paper towel rolls. So quantum computing is a lot more accessible than you might think. And here's just a stack of our electronic controls. Here's this ULE cavity that we use to stabilize our lasers. Here's another picture of a vacuum chamber. So the ion chip would actually sit somewhere inside of there. And this is just a general picture of like an optical table and all the different things that we do to control the lasers that we use to actually talk to the ions. So to wrap like that lightning introduction to what trapped ions are, so we trap charged ions in oscillating electric fields. Their motion is described as quantum harmonic oscillator. And we store information in their internal electronic states, which we control using lasers. And some things that maybe I didn't mention explicitly, we can also use lasers to interact with the electronic states of separate ions. So we can entangle two ions together using a combination of lasers. We can interact the electronic states of the ion with one of its vibrational modes. So we can have an entanglement between a qubit and a phonon, or a harmonic oscillator if you want. And we also use lasers to prepare and measure the electronic states. Okay, so now I'm going to describe something called the many spin-Boson model. So, go ahead. Is there a question?
Yeah, quickly. And before you go to the next one, how many ions are there in a trap? Can you like singularly go for a single ion trap, or there are usually a bunch of atoms within a trap? What's we're just trying to understand what's the number that like again we can singularly isolate.
Yeah, that's a fantastic question. So it's a little bit of an open question. So first of all, in our trap, we've trapped hundreds of ions. So just trapping the ions isn't the issue. The issue is that basically you have this. So like I said, everything that we do, all the entanglement operations, everything between when we try to get one ion to talk to another, is all sort of mediated off of the vibrational modes. And there's this feature that happens in the transverse direction when you're trapping ions in this linear chain. That's this thing that happens in the transverse direction where the vibrational modes actually start to crowd together. So in the axial direction, as I add more ions, so I get 3n new vibrational modes every time I add an ion. That's just a fact in classical physics. I mean, it's really simple, like write all three spatial directions. But those vibrational modes will start going farther and farther away, which can also lead to problems if they start overlapping with other, because we don't really have a qubit. Our electronic level structure is actually much more complicated than that. But the bigger issue is that the transverse modes actually start squeezing together. And so what that means is it makes it harder and harder and harder for me to like resonantly select a single vibrational mode. And that leads to all kinds of problems. But people have gotten better at using like optimal control to design like these crazy looking, numerically solid pulse sequences that actually optimize that. But I would say the last I heard, and this was like a year or 2 years ago, that somebody asked this question to Ken Brown. He said, like our limit right now is maybe 120 or so in a single trap. But I would also add to that that one of the things that we're actually working on in our lab right now, actually in collaboration with the stack collaboration with Duke and Maryland, is shuttling ions, which is super cool. So the idea would be that you would have sort of like you would modularize this, where you have maybe 5 ions or whatever trapped in a single trap, and then if I wanted to, and then you would have many of these, and then if I wanted to entangle an ion, this chain with this chain, I would just have to bring them together, do one entanglement operation, and then I can propagate that, separate them and propagate that through, and then connect other ones. And so, I mean, it's still sort of, I would say it's beyond like the proof of principle, but it's a really cool technology, and people are working on that right now. So that's like the major question for scaling up trapped ions is, how do we get past that limit of a couple of hundred ions or less? Does that answer the question?
Yeah, no, I wanted to understand the scope of it, like how many we can, and what's the limitation as of now.
Yeah, I would say like right now, in terms of if I wanted to throw, it depends on what I wanted to do, but if I wanted to use it for a quantum computer and do very controlled operations, my best knowledge, and from what I've heard from the experts that know better than me, is like around a little bit over 100 maybe right now.
Thank you.
Yep. Okay. So moving on. So I want to describe to you like the spin-Boson model, and I just want to mention, I'm just using this nomenclature because it's sort of standard. But by spin, I just mean qubit, two-level system, and by boson, I just mean one of those harmonic oscillators. And so it's many because I have many of them together. So each one of these, I'm trying to represent a spin here, and I'm just showing that the separation between the 0 and 1 state can be adjusted. That's not something you usually think about in the context of digital quantum computation, but that basically leads to energy barriers to drive. So if I wanted to couple these two together, there's an energy barrier to get from here to here. And right here, I'm just illustrating sort of the general features. This is really a family of models. I'm just illustrating the general features, which is that each one of these spins can couple to each other, and there are plenty of cases where there's really weird arbitrary topologies, because this is this is a model that's often used to describe like molecular systems or biological systems. And so you have protein structures that have all kinds of weird topologies. And then we have a coupling to like basically these individual baths of bosons. So each one of these is a collection of vibrational modes, and I can have them coupled individually so that each one of these is an independent sort of bath for every single spin, or there can be correlations. And that's essentially the model. And if I want to describe it by an equation, this is what it looks like. And that's really complicated and ugly looking. Not actually as complicated as it looks, but the point is you can kind of see just from the size of this that as you start adding more and more components, that the size and the complexity will grow very, very rapidly. And okay, this is another technical aside, but for most modeled systems, they're actually, so for physical systems like molecules, again, they're usually embedded in some sort of like protein scaffold or backbone. And they also interact with like, they're usually wet, like they're immersed in some salt, they experience like solvent dynamics and a bunch of other noise sources. And so usually the way that we treat this collection of boson is as like an infinite number of them. So it's not just coupling to 2 or 3 vibrational modes, it's coupling to literally an infinite number. And then the way that we describe it is through the spectral density. And all the spectral density is doing, if you look at the equation right here, which is maybe a little bit unreadable, I would say, but all we're doing is literally looking at a particular frequency, and then I'm looking at how much, what's the concentration of vibrational modes I have there, and it's weighted by the coupling strength to the spin system. And also if the boson path obeys some sort of practical, typically realized assumptions, then this spectral density actually completely defines the dynamics of the spin system. So often, I haven't mentioned the open quantum systems aspect of this, but often what we're interested in this context is actually the dynamics just of the spins. So that's what we would actually measure. And so, this would be like a partial trace operation if you're more familiar with the quantum information. But the point is, we treat the vibrational environment as basically a quantum, like a noisy quantum system that's affecting, that sort of is not what we're really interested in. So what's the motivation for this? There's actually a lot of motivation, but I'm just gonna hone in on this one. And it's energy transport in photosynthetic light harvesting molecules. And here's a picture of something called an FMO complex, which is involved in photosynthesis in a lot of organisms. And to kind of give you a cartoon picture, which I don't think turned out so well, but if this is a photon, the way this works is basically it's incident somewhere on this thing, and it excites it. It excites the internal molecular excitation. And then what happens is, this thing starts, it also gives it a kick, it also bumps it because photons have momentum. And then this guy will share that energy with, maybe it's next nearest neighbor, bump it, and then it'll switch it with somebody, and so on and so forth. This energy will just basically propagate down the chain. And so this particular molecule here, it really acts as an antenna and a funnel a little bit. And so what it does is it actually is very good at capturing photons and transferring them down to some area, typically called the reaction center, where they can be used that energy can be converted into some sort of stable chemical bond. So for a long time, people have always been very interested in the system A because from what I understand, it's just very easy to work with experimentally for people that actually go there and measure this thing in situ. But it's also there was also these measurements that were done actually in the building across the street from us at Berkeley by a scientist named Graham Fleming, and he was basically I think this is one of the first uses of ultra fast spectroscopy technique, or this 2D electronic spectroscopy at the optical wavelengths. What he saw was, and it's kind of hard to understand what's going on here, so I don't want to labor the point. But basically, you can measure the time dynamics. You can actually measure sort of the dynamical evolution of the system. You excite it with an initial pulse, and then you follow it with another one that does. If you're familiar with a Ramsey experiment, does something like that. But what they saw was this evolution of coherent oscillations between, I think it was one of the it was between two of these excitons that were very far apart. So it's not something that you would expect. And it was interpreted as a signature of quantum coherence in the electronic states. And so that was super debatable. It was very controversial right off the bat. Nobody expects wet, noisy quantum biological systems to exhibit quantum mechanics. And people completely went off the speculation train and started asking, did biology evolve to take advantage of quantum mechanics? Is it the case that people are trying so hard to figure out how to use, to build better and better quantum computers and quantum information devices, but nature has just figured out a way to do it already by themselves. And so it led to a lot of debate, and I think it was also a little bit escalated by the fact that in the original paper, Fleming actually makes this claim that, I don't know if it's a claim, it's kind of hard to interpret, but he says something to the fact that this is exhibiting a Grover's algorithm. So I think that might have just been bait a little bit, and it worked. And so pretty much immediately, some quantum information people, some leaders in the quantum information field, took a look at this, and they modeled something that actually had very little to do. It wasn't really based on any of the physical parameters of the system. But what they found, if you look at this plot here, is that the phasing rate is some measure of the noise that's going into the system. Basically, what they found was that as you increase the noise, the efficiency actually will initially go up. This is the efficiency of energy transfer. And on the other hand, the time that it takes to transfer that energy will also go down. And then it'll ultimately go back up again because there's these two sort of regimes. So it's not surprising over here that you get this sort of Zeno effect. And it's not surprising here that you get this sort of localization when you have some disorder in the system. But they also just happened to find that this sweet spot sort of occurred right at room temperature. And so this sort of further, I think, excited the field and made people think about this. But so after saying all that, I think the current consensus is that people do not believe that these electronic coherences actually play any role, and in fact that they pretty much disappear very quickly, and that actually what they were observing is sort of long-lived vibronic or phononic coherences, which for whatever reason is less interesting in them. But I think the point is that this model is a very complicated model, and that people have gotten very good at solving it. It's kind of hard to go through all the different, if you're not good at numerical computation. There's all different types of methods that all have all different types of limitations and regimes of validity. But the impression is that this is still a hard problem that still has regimes, maybe not physically motivated regimes, but has regimes where somebody can imagine outcomputing or computing something that a classical computer couldn't compute, or maybe outcomputing. That I'm less sure of, but I'm not an expert in that area. But nonetheless, it's a very complicated system, and it's inspired a lot of experimental work, which I'll discuss really quickly. So this paper right here, which I'll mention sort of towards the end, is the one that came out of our lab. But as you can see, like pretty much every single, or three different types of quantum information processing platforms all did this experiment. It was really popular all around the same time. And so the NMR experiment basically used this chloroform molecule to encode 4 spins. And the superconducting circuits experiment from ETH Zurich, they encoded 3 spins. And they also had this microwave resonator. And then what I thought was the coolest experiment was the trapped ion one done at University of Innsbruck, and they actually had 10 spins. So this was really, really a cutting edge experiment. And they basically reproduced this in plot with 10 spins. So they more or less reproduce the effects here. But the thing I want to—
Joseph, could I ask a question?
Absolutely.
There seems to be a contradiction in the description of your presentation as to whether or not a classical digital computer can or cannot, I don't know, do this computation more or less quickly. Let's say this particular computation, the photosynthesis. I mean, does the ion trap do a quicker computation than a simulation on a digital computer?
So at scale, the idea would be that it would. The questions here are and these are questions that I'm super interested in, by the way. So there's some people out there that really know their stuff. I'd be happy to talk to them. But the question is sort of, how big does that scale have to be? And what parameter regimes does that have to be? Are those parameter regimes that we can access? And are those parameter regimes, if they exist, physically motivated, or even at scale? Like, so if I built an analog simulator with 500 spins, something ridiculous like that, and 1,000 vibrational modes, and it worked, would I actually be able to even solve an interesting problem? Now, I would definitely be able to solve a problem that nobody else could, but would it be interesting to anybody? And there's an additional caveat here that we can definitely measure a lot of properties of the vibrational modes. For example, the Fox state, the phonon occupation number and stuff like that is fairly easy for us, although intensive. But we don't have as much control over the vibrational modes. We can prepare them very well in their ground state, and also sort of exotic states, like box states are very simple for us to repair, and display states, people have been doing that for a long, long time. So I think that's an interesting feature that we can look at. But yeah, does that sort of answer your question? I think I'm sort of going off on a tangent, but does that sort of answer your question?
Yeah, thank you.
Okay, so yeah, I wanted to make the point, maybe this is hidden a little bit here, but so I want to make the point that I'm counting the number of spins in these systems, but not the number of bosons. And the reason for this is that none of these models that I just showed you are actually spin-Boson models. All they did was put 10 spins together. They didn't couple anything to coherently to a vibrational mode. And so what they've done is really like a semi-classical approximation, where they've taken sort of they've modeled what should really be a quantum spectral density with some similar classical spectral density, and that'll never be a particularly challenging task, because if I can if I can create some stochastic process and sample from it efficiently enough to actually program my quantum simulator, then I'm always going to be able to do that on my classical computer. Unless you get to the point where you actually have a large enough system, period, before you start adding this noise that can't be calculated. So in that case, it's kind of cheating a little bit, in my opinion. So in particular, those models can't account for important effects like temperature and just reiterating that point that they'll never be more difficult than to calculate the underlying system. Okay, so now I want to briefly talk about the experiment that was done in our lab, and so it's kind of like on the other end of the spectrum. So these experiments I just talked about, they had a lot of qubits, or more qubits, and they also had, I didn't show them, but they also had fairly complicated. In most cases, they implemented at least Lorentzian spectral densities for the coupling to the environment. We have something that's extremely simple. In fact, the simplest possible many spin boson model you can possibly make. One spin, essentially, even though I'm showing 2 qubits, we work in the one excitation subspace, and a coupling to a single vibrational mode. And I just wanted to go through this example really quick from the paper, because it's fairly simple, just to kind of give you a feeling for that equation. But so this sigma x is an entangling gate between these two different ions here. And basically what's happening is I'm starting off in some state SD, or down, sorry, it's like 0, 1. And then I'm oscillating between 0, 1, and 1, 0. So energy is kind of jumping back and forth between these two sites. And then what happens is if I increase this delta, then I end up getting that energy transfer becomes, so I'm starting to experience this localization. And I can't really resonantly excite that energy, that interaction anymore. So then what's interesting is I can then take this coupling to the vibrational mode that just couples to a single ion. I can turn it on, and if I turn it on with just the right parameters, then I can actually get efficient energy transfer again. So this is something that you can totally solve on your computer at home very, very simply, but it's just this interesting effect. And this is something, for example, that you won't see in these other papers. An intrinsically quantum effect where you're actually having a coherent interaction with this vibrational mode that's sort of mediating interaction between these two ions. Yeah, and so one thing that I want to point out here, I don't think I point out anywhere else, is that also in these simulations that we have an extremely high control over all these parameters. And in particular, this new effective is not actually the oscillation frequency of the vibrational modes that we have, like the intrinsic oscillation frequency. This is actually completely controlled by a laser detuning, because we implement so this is in some rotating frame, and we implement this interaction with a 2-photon transition. So we, in principle, can make this all the way down to 0. And people have always been interested in that, because you can get to a place where the quantum Rabi model just completely it already becomes very difficult to calculate. You can do weird things like excite 2 atoms with a single photon, or vice versa, and things like that. Okay, so this leads to another problem. Our implementation does, I mean. How do we scale up to real world size problems? And so if you look at like what would represent our spectral density, it's just literally a single peak, right? We have a single vibrational mode. It has a well-defined frequency. So it is like a discrete single peak. So if I look at an actual spectral density from a molecule like that FMO molecule I showed before, this is what it looks like. So how do I go from, so if this is a proof of principle experiment, how do I go from this to something that can actually hope to do a simulation like this, for example, in 2 or 3 years? And this is sort of the best we can do. It's not clear at all what this would mean or what the significance of this would be, or how well it would model it. So we kind of run into a problem there. And maybe we can put 30 modes in this if I'm being super optimistic and interact with them. That would be like really the cutting edge, top of the line at that point. But even then, I don't really have enough to reproduce this structure. So fortunately, there's it's like this new idea came out that was published by the Flenio group. And they noticed that basically I can do Doppler cooling, or I can continuously cool the vibrational modes to a particular equilibrium temperature. And if I do this, so I'm denoting that in bar. And so basically what I'm doing is I have one spin coupled to one vibrational mode, but then I'm constantly damping this to a particular temperature. And if I do this, then you can show rigorously that the dynamics are to extremely good approximation, exactly the same as if I was coupled to a continuous infinite number of vibrational modes, reconstructing that same spectral density. And basically the conditions just boil down to like some very basic things like that I have to have Gaussian states, which are just like normal thermal states that we almost always start off with, or even coherent thermal states or display states, and that also the spectral densities match. And as long as that's true, then this will always be true. So the only problem with this is that in order to implement something like this in our lab, we would actually have to trap an additional ion species in our trap. We would have to, because we're going to constantly be cooling this thing, it's going to be scattering photons all over the place, and we just have to make sure that those photons are not resonant with any of the other atoms. And so that's expensive. It takes a long time. You have to break vacuum, and to get to the vacuums that we have to basically just bake our traps at like a couple hundred degrees for weeks and weeks until the pressure finally goes down, while we're pumping them out with turbo pump. So this isn't totally not something that we're really looking forward to doing right now. And it's also, I think, been a barrier because there's been a lot of cool experiments that have basically come out, or theoretical proposals for experiments in trapped ions that have sort of talked about using this kind of damping to create more or less to take advantage of the fact that it creates a Lorentzian Lorentzian spectrum, excuse me. So this is the new idea that I had like just recently, since I'm on quarantine. All I can do is read theory papers. And so basically I can do the same thing, except for instead of cooling this thing continuously, I can basically cause the energy levels to wobble, which is like in some sense a really unphysical interaction. It has to do with the way that I implement that coupling in the first place. So I'm not even causing, I'm causing the effective, that new effective, since that's controlled by laser tuning, I'm causing that to wobble. And again, it's really unphysical. The sort of coupling we had with the spin-Boson models, generally speaking, if I had, if the vibrational frequency was to fluctuate, what that would actually, it would cause like this period of phasing, but it would also cause terms that led to like heating. So this is like a really unphysical model. It's really crazy that it reproduces the same thing. This I'm sure of at this point, but I just don't really know what the implications are. And so I'm pretty interested in seeing what we can do with this. But the main thing is that it's incredibly easy for us to implement. So we don't need new lasers. All we need to do is add white phase noise onto the RF that we use to control our to modulate our lasers. So it's like really, it's something that we can do extremely easily and get these same results. So yeah, so I mentioned that it can be applied with the white phase noise. And so another thing that we can do is initialize. So if we had multiple modes, we can initialize them to all the different temperatures. So that's something that's not possible with the laser cooling, because the laser cooling basically, it's got a very broad frequency content, and it's hitting every single vibrational mode that it has projection on. So if the ions, if the ions are in a chain like this and it's going this way, then it's cooling all the ions that vibrate like this. But it's not doing anything to these vibrational modes or these vibrational modes. But so you'd have like maybe 3 choices of different temperatures. But with this, we have complete arbitrary control. But I actually have no idea what that means. I don't even know if that leads to something physical. But that's something that I'm really interested in and haven't had a chance to think about much yet. What I wonder is, okay, what if I trap a single ion in the trap, which is extremely easy for me to do, and then I just throw 10 vibrational modes in there, which is also very easy to do. Now I have a huge Hilbert space already. I already have a Hilbert space that there's no way I can calculate on my computer at home. So can I do something interesting with that? Can I do some like sort of thermalization experiment? I have no idea, but I'm really interested in hearing, would be very interested in hearing anybody's ideas on that sort of thing. I guess like my big, something that I'm really interested in thinking about is what's the, in the spirit of like analog quantum simulation and taking advantage of like the things that are easy for us to do. What is, if I can trap one ion, I can drive it extremely quickly and I can couple it to like pretty much right now 10 to 20 modes. The only limit we have is literally the number of like acousto-optic modulators that we use to control the frequency of the lasers. So, and that's just a matter of buying them, waiting for them to come in. So is there something I can do there? Because what I know for a fact is that the complexity, at least in the very naive sense, the Hilbert size, the Hilbert space dimension blows up, right? If I have 30 modes, I have 10 to the 30, and it takes probably at least 10, maybe depending on our temperature, 10 to 15 levels to simulate that reliably on a computer. I mean, we're already at a point where like this is something that's pretty difficult. Yeah, so I'd like to know a lot more about that. And I also mentioned that I don't believe this is unique to ion trap limitations. I think that also superconducting circuit people can do this right away, right now too, just as easily, probably more easily because they're a lot better at doing frequency mixing. And then this is from a recent article that kind of talks about using trap.
Can I ask a question quick?
Yeah, of course. Go ahead.
You said you were using calcium ions right now, right?
Right.
Can you change the ions, like maybe iron, or like why calcium is what I'm trying to understand.
Okay, so so first of all, that's a great question. So in general, like the atoms that we choose tend to be atoms. I forget the families in the periodic table. They tend to be atoms that such that once I take one so they have 2 electrons in the valence shell or the outermost shell. So if I take one of them off, then it's hydrogenic. If you use that term, it looks like hydrogen, and we understand hydrogen very well. That's not really an absolute necessary requirement, but that's sort of what motivates the choice for these different ion species. But that being said, the reason that we specifically use calcium-40 is basically just because Hartmut Hafner, my PI, he's from the University of Innsbruck. He's like a Rainier Blot disciple, and he uses calcium-40 and also calcium-43 right now. But they have hyperfine levels. But there are definitely calcium-40 has basically the advantage that it's sort of easier to work with, but it also has disadvantages like the fact that we have a finite lifetime. So we don't, which can get around a little bit. But so the lifetime on our qubits is 1 second, whereas I can work with hyperfine qubits that have lifetimes of 10,000 years or whatever. Not so much a limiting factor for us right now, but still,
Okay, thank you.
That's your question. Yeah, it's really, I think for the most part, it's a little bit arbitrary. I think people start new groups and they kind of use whatever, tend to go to whatever the ion species was that they were using in their old group, But there's definitely pros and cons. I think, for a variety of reasons, I think probably ytterbium is superior.
Okay. The reason I asked, I'll just say, I mean, maybe this is pretty dumb, but you were trying to understand if any other way you can introduce dephasing noise, right? Instead of you didn't have ability to put in a lot more lasers because it'll take a lot more pumping in and out time, then cooling, and then basically you'll have to change the architecture of your experiment. So you were trying to introduce a wobble in your vibrational modes. I was just thinking, like if we use some other ions or some other mechanism, can we use magnetic field as something to introduce some kind of a destabilizing or dephasing noise? Is that something that can be tried or has been tried? Maybe it's.
So Yeah, I mean, so just in general, I think there is an open area there to think about what else, because first of all, like the intuition for the fact that the phasing does the same thing as the damping is completely bizarre to me. I mean, I mean, they both conserve energy and everything else, but it just doesn't seem like it should work. And it's still difficult for me to wrap my head around that. And I'm not saying that there's any super significance to that. I mean, the point here is that the dynamics of the vibrational modes are completely wrong. What's preserved is just the dynamics of this. So if I just measure the ions and I don't care what the vibrational modes are doing, the environment will have the same effect on dynamics. That's all I can say. But magnetic fields won't work because like it's the electric field. We're actually using electric fields to trap these things, and that's that. The magnetic field interaction is extremely weak if for the atoms. But you could imagine. I mean, a reasonable thing to do is to imagine actually introducing electric field noise. That's a major source of noise for surface traps because they're much closer to the surface, and there's all kinds of like random electric field noise there. But this runs into the same issue that basically if you do that, you will get terms like this dephasing term, but it also comes with heating. You also actually will, so you won't conserve energy. So it won't reproduce this exact Lorentzian spectral density or necessarily anything that's useful. But just, yeah, in general, looking at different ideas for how to cause dephasing is definitely, I think, is definitely interesting, I think. And also, another thing that I think is interesting would be to think about actually, putting in sort of an exotic classical modulation rather than white phase noise. I could put like some maybe exotic classical modulation. And if I do that, could I build even more structure, or is it just complete nonsense? I don't know. I haven't looked into it yet. That's another interesting thing.
Yeah. Thanks.
Yep. Okay. So I'm getting close to the end here. But what's next? Basically, one of the things I'm looking for now is probably just to implement this for a single ion. I mean, the backup plan, I guess, is we're just starting to get back in the lab now, but would be to actually just do a demonstration of building a tailored, quantum noise spectrum. So people have done this in the past with, have come up with prescriptions for doing this classically or for classical noise spectrums. So I think this is worthwhile and maybe a way to introduce this in a publication. But there's also some other interesting things, like there's this dissipative phase transition, the open quantum Rabi model that the theory has been prescribed to do this, but it uses, it requires damping of another ion species. And so now we have the ability to do that without having to get another ion species. And like I said, I'm sort of interested in just questions. I'm interested into a lot of questions about, what happens if I just take one spin and couple it to like 10 or 30 Moses. I think that's something that we can do right now. If I tried to put 30 ions in my trap, there's no way that it will work because we just don't have the infidelity sources are too high. But we have very stable vibration. The trapping potential is basically what determines that. But also, if we're just working with a single ion, we can go into this rotated basis where we can do everything with single photon transitions, which just means that the coupling strengths are much faster. And so we can run experiments that really take, less than a millisecond, significantly less than a millisecond. And for us, that's well within like where everything in our system works pretty well. Yeah, so I'm pretty interested in, I'm pretty interested in seeing what we could do with that. And like the question is like, also, moving away from this idea of like the dephasing, also can we ask questions about like, creating really difficult probabilities? I'm completely speculating, by the way, right now. I'm not a theorist, but like, can we think about the ions actually mediate interactions between the bosons? So we get some entanglement there, mediated through the ions, and we can turn up the coupling strength very, very high. So we can make that rather strong. We also have sort of an always-on coupling between certain vibrational modes. That comes from the nonlinearity and the Coulomb repulsion. And we have, there's some other methods for actually creating direct vibration interactions, which, I don't know, it just seems like there maybe is some cool, it seems like there's a potential for having a lot of complexity here in a rather simple, with rather simple technical requirements. But, the major question is there anything interesting that we can do? And I think, yeah, I don't know if I think I glossed over this plot here, but just to make a point of this, this right here is like this MCTDH. I think this is a multi-configurational retrieve. I don't know, but this is like the best method, I guess, for sort of solving the problems with a lot of vibrational modes. And it's really fuzzy here because I guess it's actually kind of tricky to find the right basis to actually run this in, so you actually can solve things more efficiently. But if you look at this, like this is like 30 modes right here, and what this red is saying is like the best classical algorithm that you can think of to use. And so at 30 modes, you're already like, approaching over a terabyte. And so then the question is, if I did this with an open system, so if we actually did this where we were doing this damping, does that mean that this scales quadratically? Is that 1 terabyte squared? Is that how much memory I need? So I'm just wondering how close we are to actually being able to do something really challenging, which is obviously only part of the description. The other part would be like do something interesting. But this is all very much so speculation, to be clear. I would normally not speculate so much in a public talk like this, but I just want to kind of encourage feel free to, I don't know if I put my email address up here, but put it in the chat, I guess. But anybody that's interested in talking about these ideas, I'd be happy to connect with you. So I'm almost done. I'm ready for questions here, Mark. But like, do I have time? I know I'm running a little bit long here. Do I have time to like advertise sort of a little amateur programming project that I have?
Can you make it quick?
We make it like 5 minutes, probably.
Sure.
Okay. So I might have to reshare my screen here. Did I lose everybody?
Nope, still good.
Okay, so I have this program IronSim.jl that I made. It's kind of like I guess an analog simulator if you want. If you've ever used something like Qtip or quantumoptics.jl, it's just normally they provide you with sort of basic objects like qubits and harmonic oscillators, and you can build things up. And that's what a lot of people in our lab and stuff actually use to do these simulations. When we're just testing things or making sure whatever the results we're seeing in the lab are correct. But it seems like there's a use for a higher level of abstraction, just because, I always find that I'll write a notebook and I'll spend like 2 hours doing it because I haven't wrote a simulation in a while. And then, I'll find out that I made a bunch of mistakes or I'll be missing a factor of 2. Sometimes I'm really interested in quantitative results. So I just kind of wanted to streamline all that. And so I made this program here. And again, this is total amateur hour. I'm not a programmer, but I have like this website that has some examples of the code and everything. It's very much so like in the preliminary stage here. So there's no documentation up yet, for example, but I do have an examples section where I actually walk you through basically some ideas in physics in general and what we're simulating and how it works. And basically what this is doing is just, I use the quantumoptics.jl backend, which is really just a small wrapper around differential equations.jl if you're familiar with that. But the effort that I've done is just to make a time-dependent Hamiltonian function that spits out values very quickly or as fast as I think I could. But what I'd be really interested in is, so first of all, I'd love feedback on this. And if you go to the GitHub here, you can there's an option there's this discussion thing I think that's open now on GitHub, but there's also this getter that nobody's used yet. But yeah, if people, so I haven't worked on this for a while, but I do want to get back into it. But if people would take a look at this, it's maybe a good way to learn about trapped ion physics, like the simple things. If you have like a computer science background and you wanted to get into this, or if you're an ion trapper and you think it might be useful, I'd love just to hear feedback. If this is, if this ended up being, so I think it's more of like a basic prototype right now, but if this ended up being something interesting for the trapped ion community at large, and definitely I'd be interested in doing a publication. But at the very least, I would just, I'd love to hear any feedback, even though the feedback is this is garbage. I have no use for it, and it's impractical, because I really just built it for myself for one specific purpose. So there is a very open question of whether it's useful at large. But yeah, so please, if you have a chance, take a look at it. You can run code. You can technically run this Jupyter book stuff on the cloud. It takes a while to load because of Julia, that pre-compilation time. But yeah, and there's some stuff on, so at some point there'll be some more pedagogical stuff here, but there is some stuff on like this is showing you the Hamiltonian and how to actually run a Mollmer-Sorensen gate, which is what we use. This is a basic entanglement gate in trapped ions that we use to build up like CNOTs and stuff. And it shows you also the simulation of like that vibrational axis and energy transfer experiment I showed you. and some other cool stuff like that. But yeah, with that, if there's any questions, if we have time left, if not, feel free to email me I'll just put it in the chat really quick. I'm at jbroz@berkeley.edu. Okay. Yeah. So, any questions?
Thank you so much, Joseph.
Joseph, I apologize in advance. Can I ask an irreverent question, which I'm sure you've gotten before?
Oh, go ahead.
Are you related to and I'm an old guy, so I remember him. Are you related to the historic figure who has your name?
No, I love that you asked me that, because like for a long time I would always start off with that joke and nobody ever got it.
Yeah, well, I mean, you have to be a certain age. He died about 40 years ago. So
yeah.
You're not related to him.
No, I don't think so. I don't know a lot about. I know that he was like a dictator, right? But he was a benevolent dictator. He was well loved. He had the most successful resistance in World War II against the Nazis.
Well, some people called him tougher than Stalin. So he was pretty cruel, but he was closer to the West than any other communist dictator. But is your family Croatian? I believe the name is Croatian.
Yeah, I'm not sure. We're from around somewhere around from there is where that name comes from.
Yeah, because his father was Croatian.
Yeah.
I know that, yeah. I'm sorry. This has nothing to do with quantum.
Oh, no, I'm happy to hear it.
So I see a question in the chat from Thomas Clark. Thanks for the talk. Cool website too. What advice would you offer for an undergrad looking to get an introduction to ion traps and photonic superconducting models for quantum computing?
In terms of like resources, so do you have an ion trap lab in your institution?
Thomas, would you like to clarify? No, not at the moment.
Well, I mean, if you wanted to get involved, so I think that the website I showed you in that code is actually fairly accessible. It's not as difficult as it looks, and I would be happy also to walk you through that if you wanted to. But basically, it's a numerical implementation of really basic ion interaction. So I think it would be a great learning experience, and I would be happy to help you with that as much as you want. That's one way. I can't think off the top of my head of like any like great textbooks. The thesis. So I mean, I guess I would recommend the thesis that's always recommended to us that you can find is like the original, not the original, but like Christian Roos. And I'm biased because my PI is from Germany, so it's all European stuff. But so Christian Roos, if you look up his thesis, it's great. I think there's a really advanced but very comprehensive and old review article from Liebfried that has it all. But I still don't grasp most of it. And another honestly, I would go to like I always just go to the Innsbruck webpage, University of Innsbruck, and I forget what the name of the formal name of like the trapped ion group is there, and I just look through their theses, and there's always like a ton of really good ones, and I'm sure also the theses at like Monroe's group and our group, of course, our lab. And if you're in the area, if you ever want to like get a tour or whatever, you can also just contact me. Did I put my email just there?
Yeah, good. Are there any other questions? Really cool talk. I studied physical chemistry and wanted to know more about quantum computing. Do you have any suggestions for going further?
Well, and I think physical chemistry is a great start. So all the theorists that we work with are physical chemists, by the way, and they're like the smartest people ever. Yeah, I think, I'm sure you've heard this before, but Nielsen and Schwang, that's the book I learned from. I think that it's old now, but it has all the basics, right? Can't really go wrong with it. Yeah.
Good. Are there any other questions? Cool. So thank you again, Joseph, so much. And I think that concludes the talks for 2020. But I'm looking forward to seeing all of you after the new year. Happy holidays and stay safe, everyone.
Happy holidays, everybody.
Bye.
All right. Thank you. Bye. Happy holidays. Bye.